solid or liquid. But what we measure as part of our monitoring program is dry PM. Okay, we don't measure the liquid phase, we measure only the dry PM. Okay, PM refers to particulate matter. Then we have this SO2, NO2, ozone, carbon dioxide, no, sorry, carbon, not carbon dioxide, carbon monoxide, and NH3. And also we have some VOCs like benzene and PAHs like benzoyapyrene. These are all forms the list of criteria pollutants for the case of India. These all needs to be monitored by the regulatory agencies. Here in India, Pollution Control Board is a regulatory agency, while in the states it is Environmental Protection Agency is the regulatory agency. Okay, this is the list of criteria pollutants. Okay, then why we need to measure? Why we need to measure these pollutants? See, there are so many aspects to it. Like to understand and report at what levels the air pollution is. Also to understand and identify what are the major sources that are responsible for this pollution in the atmosphere. Also, to assess and track the effectiveness of mitigation programs. As part of mitigation, governments will bring in a lot of mitigation programs, and to see whether the mitigation program are really fruitful or not. Also, to provide data to researchers and the community. Like we have a lot of regulatory measurements and their data is publicly available and the researchers can use that. Also to assess the health impacts of air pollution. These are some of the needs for measuring air pollution. And here in India, we have this pollution control board, which measures air pollution and keeps the data in public, and we all can use the data for various purposes. Okay, then if you want to measure, there should be some technique to detect air pollution. Okay, there are some standard techniques. There are some standard techniques through which these air pollutants can be detected and quantified. Okay, for particulate matter, I listed three, which is gravimetric, beta attenuation, and tapered element oscillator microbalance. And every pollutant have some standard technique to quantify and detect and quantify. These techniques also include some techniques are manual techniques and some techniques are continuous. Like two types of measurements can happen. One is time integrated measurement. We also call as manual measurement, where we collect sample for a particular stipulated amount of time and do a offline measurement on the sample. And another type of technique is real time, like continuous and real time measurements can happen. Like we can get data for every 1 hour, every 4 hours, or every half an hour kind of thing. Okay, these measurement techniques here, what I listed here, they include both manual and manual means time integrated or and continuous. For particulate matter, gravimetric technique is a manual technique. Like we collect PM sample, either it is PM 2.5 or PM 10. We collect the PM 2.5 or PM 10 sample over a filter paper for stipulated amount of time, and then we take back to the lab and we do weighing of this filter paper before and after the sample collection, through which we can determine how much mass is accumulated on the filter paper. This is the gold standard technique we call. This is also called Federal Reference Method, FRM method by called by US EPA. And these next two, beta attenuation and TEOM, we also call this as a tapered element oscillating microbalance. These two are measurement techniques which can be capable of giving continuous data. Like every 1 hour or every half an hour, we can get the measurement of particulate matter. Beta attenuation is like how much beta particles. Beta particles are nothing but high energy electrons. How many high energy electrons, how much of high energy electrons are being absorbed or attenuated by the PM that is deposited in the filter tape. Yeah. And tapered element oscillating microbalance is also another technique where the there is a tapered element upon which a filter paper will be mounted, and as the filter paper gets loaded, there will be a change in its oscillating frequency. Through through measuring the oscillating frequency changes, we can estimate the PM that is deposited on the filter paper placed on the tapered element. These are some of the techniques that we use to quantify particulate matter. And when it comes to ozone, we have this chemiluminescence and UV photometry. Chemiluminescence, as the name suggests, luminescence is emission of light, and chem is chemical reaction. Through some chemical reaction, it emits light. By quantifying that light, we can estimate how much ozone is present in the atmosphere. At the same time, UV photometry is how much of UV light is being absorbed by the ozone. These two methods can be used for estimating ground level ozone. We all know ground level ozone is a secondary pollutant. No process emits ozone, but it is formed through photochemical reactions. And again, carbon monoxide, we use NDIR, non-dispersive infrared spectroscopy. Again, how much infrared radiation is being attenuated by the carbon monoxide. That gives you the amount of carbon monoxide, CO, that is present in the atmosphere. For nitrogen oxides and sulfur oxides, I mentioned this Jacob and Hoxer modified method and improved West method also. These two methods are for manual sampling. Like through impinges, we collect the air sample through bubbling methods, and in the lab, we do some certain chemical reaction through which the solution changes its color to violet, pink. There are some colors that changes into colors, and through spectroscopically, we can measure the intensity of the color, and that we can, through which we can estimate the amount of NO2 or SO2 present in the atmosphere. This gas phase luminescence, again, I said, like I explained, what is luminescence? The same way, gas phase luminescence can be used for continuous measurements of nitrogen oxides, which includes NO, NO2. Sulfur dioxide also, we can use UV fluorescence. You know what we know what is fluorescence. It absorbs a known amount of UV light and again re-emits some ultraviolet ray. This is UV fluorescence. For lead is very toxic pollutant. For lead, we generally use EDXRF, X-ray. EDXRF, X-rays will be absorbed. X-rays will be used to knock out some of the inner shell electrons, and from outer shells, some transition will happen, through which again some X-rays will be emitted, which we call characteristic X-rays. Due to by measuring the characteristic X-ray intensity, we can quantify lead. Okay, these are the standard techniques we use for measuring all these air pollutants. Okay, then we call reference grade instrument, regulatory grade instrument. You might have heard about these kind of terms like reference grade measurements. What is reference grade measurements? Okay, in the previous slide, I listed all the measurement techniques that are very standard in quantifying the air pollutants. Okay, what is reference grade measurement? If we use the approved or reference or equivalent methods, which I listed in the previous, okay. Also, when we employ high precision instruments, high precision means the error in your measurement should be as low as possible. And if you follow strict quality assurance and quality control protocols, like these instruments need to be calibrated at a certain frequency. Also, these instruments need to be cleaned, need to be the consumables need to be replaced. We call all these things as maintenance. At the same time, controlled sampling. As I said, like PM, we always measure dry mass. Okay, for dry mass, what we need to do from the sampled ambient air, we need to remove the moisture. For that, we use heating techniques. Okay, heaters we use. At the same time, all these gas pollutants also need to be what you call them. The moisture needs to be removed. Otherwise, the moisture will interfere with the measurement technique. Okay, that's why we need to we need controlled sampling. Okay, if you use all these techniques and if you follow proper QA/QC protocols and if you employ high precision instruments, then the data that is being collected, we call it as reference grade data. and the data can be used for compliance, enforcement, for legal purposes. Also, the data set that is collected by using this type of instruments and this type of procedure can be used for national statistics also. Okay. This is called reference grade measurements. Okay, now you can see a bunch of, I collated a bunch of instrument pictures from internet. Okay, and you can see the first two ones are particulate matter measuring instruments. Okay, these are called BAMs. You can see BAM 1022, BAM 1020. The 1020 and 1022 are different model numbers. BAM stands for beta attenuation monitor. Okay, it employs, this instrument employs beta attenuation technique to identify or to quantify the particulate matter. Okay, it is having some consumables that it needs, like filter tape. Also, you can see there's a you might not be identifying it here from this picture, but these BAMs has a heated inlet, a heater around the inlet. Okay, on the right side, you can see a bunch of analyzers like CO analyzer, NO, NOx analyzers from different companies. Okay, these analyzers will measure CO, NOx, SO2, CO, or NH3, all those gases pollutants, employing the standard techniques. In the last right corner, you have this gravimetric measurement. I just pasted this picture to show how a filter weighing generally happens. You can see a small microbalance where we put the loaded filter on the microbalance to weigh the filter paper. We do this weighing before and after the sampling PM, and the difference will give you the mass that the how much of PM is deposited on the filter paper. Of course, this technique also needs a lot of protocols to be followed. Like, you need to desiccate the filter paper, you need to have a conditioned room, you need to have a vibration free. So many protocols we need to. When we employ all these protocols and when we use all the standard techniques and we use these high precision instruments, then we will get reference grade data. Okay, these reference grade instruments, USEPA gives a label called FRM and FEM, Federal Reference Methods and Federal Equivalent Methods. Okay. Yeah. Now, here I'm trying to say, like, all these instruments that I have shown in the earlier slide, um, they need, they are mostly rack mounted and sheltered, because in order to use those instruments, all the instruments need to be rack mounted and these racks should be sheltered. It requires some uh, conditioned atmosphere, like they need a temperature, like we need to maintain the temperature in the shelter, we need ACs, we need air conditioners. At the same time, they require conditioned power, means like without leakage currents, the earthing should be good. All those requirements are are there for these instruments. Okay, they are mostly rack mounted instruments. They are not portable and they are not easy to carry, or they are not easy to they are not for rapid deployment. Okay, these instruments require either racks, and these racks to be put in a shelter for optimum operation of these instruments. Okay, you can see how a shelter looks like. On the right side there is shelter where you will inside the racks, how the racks will be on the left side image. Okay. Now every method, every monitoring method or every measurement method will have its positives, negatives, pros and cons, trade-offs, limitations, everything. Okay. We can understand from the amount of accuracy, the amount of precision that these instrument data have always comes with a cost. Okay. The instrument, these instruments are generally costly, not only in terms of the initial cost, but also the maintenance cost. Okay, the operating cost, capex and opex, both are high, because in earlier slides I mentioned that these instruments need a regular calibration and routine maintenance. Okay, they also need some consumables to operate. Okay, all these adds up to the cost. Initial cost is also high. At the same time, we need some regular calibration. The calibration can be a flow calibration, span calibration, the photo detector calibration. There can be so many calibrations that are involved. Okay, and infrastructure and maintenance intensive. Why I say this maintenance intensive on infrastructure? Because you have seen in the earlier slide, it requires some shelter. Okay, if you want to construct such shelter, we need some space. At the same time, we need some unobstructed space, because we need a free flow of air such that the measurement is not biased. Okay, we need continuous power supply, not only for the instruments, for the ACs, air conditioners also require this power. At the same time, we need conditioned power, like without leakages in the without proper earthing. Otherwise, the instruments can go bad. Okay, and obviously, to do all this routine maintenance, calibration, and installation of these things, we need skilled technicians. We need skilled technicians. It is not a plug and play kind of device. These instruments are not plug and play kind of devices. We need skilled technicians. Okay, air condition centers already I mentioned, and routine calibrations I already mentioned. Every instrument is different. Every analyzer or every monitor is different, and it has its own needs. We need to see what instruments need to be calibrated at what frequency, and we need to cater to that. And I in the previous slide you have seen these instruments are rack mounted. They are huge, and they are not for mobile monitoring kind of application, but they are only for fixed site monitoring, or otherwise we call it static monitoring. We use most of devices for static monitoring. Okay, this due to these things, it limits scalability. Like we due to the cost and due to the infrastructure demands, we can't simply have n number of devices purchased and deployed. Okay, it is both costly, at the same time resource intensive also. That's why this all these things limits scalability. Okay, these are the trade-offs for uh, reference grade instruments and reference grade measurements. Okay, now we will come to the low cost sensor topic. Before going into the low cost sensor topic, I just want to talk about what is reference grade instrument, what is a criteria pollutant, what are the positives and negatives of regulatory measurements. The positive thing is it will give the regulatory measurement will be very accurate, very precise, and they can be used for any regulatory, legal, and enforcement purposes. But the trade-off is high costs, infrastructure and maintenance intensive, and limited mobility. These are some of the trade-offs. Okay, now we are going into our topic, the low cost sensor. Okay, now the trade-offs to overcome all those trade-offs, these low cost sensors, they overcome all those trade-offs. But again, as I said, every monitoring method or every measurement method has its own pros and cons. Okay, here I will always start with the pros, and I will come to the cons, and I will explain all the limitations of low cost sensors also. Okay, what is the um, advantage of this low cost sensors? Okay, the first thing with reference grade monitoring is high cost. The low cost sensors, as the name says, is low cost, or sometimes we call as affordable cost. Okay, affordable monitors, low cost sensors. And these sensors are very compact, means they are small in size. They are portable, easy to handle. Okay, and easy to operate, easy to install, or easy to collect data. Okay, these are the major, the first one is the major advantage with the low cost sensor. First thing is affordability in terms of operational cost and in terms of um, maintenance and capital cost. And compactness, the portability. The portability brings in a lot of applications. I will come to that in the next slide. And the next thing is high resolution. Here, high resolution, by high resolution, I mean high temporal resolution. Often these high-end instruments or regulatory grade instruments will give 1 hour averages or half an hour averages kind of a frequency. But these low-cost sensors are capable of providing high temporal resolution measurements. Like we can get 1 minute averages. Some sensors are able to give even 6 seconds, 10 seconds, 30 seconds averages also we can get from this low cost sensors. Here resolution means in terms of its temporal resolution they are able, and this high temporal resolution is can be useful in some cases. Okay, again that I will come to the next slide. and uses simplified sensing technologies. Here, it is very important to understand the sensing technology that these low-cost sensors employ is different from what we discussed as standard techniques or recognized or USEPA methods. Okay, these sensors use some different sensing techniques which are more simplified compared to the standard techniques that we listed in the earlier slides. Okay, and you can see some of the low cost sensor modules that I pasted here at the bottom of the slide. Okay, you can have this aura shore, air beam, atmos per player. These are different low cost sensor assemblers, and these I call as low cost sensor module. Okay, uh, I will come to the sensor next. Okay, now coming to I explained all of this mostly, but by coming to the key advantages and applications of these low cost sensors. First is cost effectiveness. Okay, this cost effectiveness enables dense monitoring network. Like we can deploy tens, hundreds of low cost sensors because they are cheap and they are portable, right? We can afford. Okay, suppose if we have a uh, these low cost sensors can be anywhere between few hundreds of dollars to few thousands of dollars. Okay, there can be anywhere. Again, depend the low cost sensors have a lot of components. Again, I will come to that part at the end of the presentation. Okay, due to this cost effectiveness or cheaper cost, we can afford more sensors and we can establish dense monitoring networks to capture spatial variations in air pollution. We all know that air pollution has large spatial variability compared to any meteorological parameter. Like unlike temperature, unlike humidity, air pollution varies very rapidly in space and time. Always you having dense monitoring network is an advantage to understand some localized patterns in air pollution, uh, hotspots kind of thing. Okay, then this reduced infrastructure requirements. Okay, in my earlier reference grade instrument, I explained that it requires a lot of infrastructural needs. Okay, like space, power, shelters, ACs, all those things. But here, the low cost sensors doesn't require all of these infrastructure needs. Okay, we have very little requirement. Just we need small power, like uh, how much we need for mobile charging. That small power is enough to run a low cost sensor. And due to its portability and flexibility, okay, they are very small in size. Okay, we can go for rapid deployment. Like very quickly we can install these sensors, or very quickly we can deploy these sensors. They are mostly plug and play. Like you just plug it and just switch it on and they start measuring the pollution levels. A mobile and personal monitoring. In the previous slide I mentioned, due to the due to its size and due to various factors, uh, reference grade instruments are mostly used for static measurements. But here, these low cost sensors, due to their portability and flexibility, they can be operated on batteries also. Due to this flexibility, we can use this low cost sensor for various applications. In addition to static or fixed site monitoring, we can use it for mobile monitoring. Okay, on mobile platforms we can install, like in on a bus, on a truck we can install, and we can measure air pollution, and we can understand what is the spatial gradients. At the same time we can use them for personal monitoring, like how much we are being exposed to, how much amount of pollution that we are that is being deposited in our lungs, how much of particulate matter, all those things we can do using personal monitoring. They are mostly intended for health studies and at the same time commuter exposure kind of studies. All this is possible with low cost sensors due to their portability and flexibility. And community engagement. As I said, these we don't need a skilled personnel to install these devices. That's why we can engage community, we can engage citizen scientists in these low cost sensor deployments. Like we can give the sensor to them and you can just tell them, okay, put it here and just switch it on. It starts working, it starts collecting data. That's why these features will have these applications. And as I said, like high temporal resolution data can be used to detect episodic events. Suppose there is a small pollution plume, or there is a small event that is happening for few tens of minutes. Okay, you have high resolution measurements. If you have those kind of episodic events can be captured. In contrast, in your reference grade instrument, what happens is we will get hourly averages. Mostly BAM will give you hourly averages of PM2.4, PM10. Then these episodic events or these variations will be averaged out. Okay, that's why high temporal resolution is useful in identifying episodic events. At the same time, traffic peaks. Okay, because sub hourly data can give you better resolution, better information about traffic peaks. Also, one of the main advantages, these instruments or these low cost sensors work on Internet of Things. We all know what is Internet of Things. Things means here the things are nothing but our sensors. All these sensors are can be connected to internet. All these networks and network of sensors can be connected through internet, and all the data can be accessed through cloud storages, all those things. That's why you no need to go to each and individual sensor and download the data. We can get the data over internet, and most of these sensor vendors give you personalized dashboards to check whether your sensor is collecting data, whether the sensor is online, whether the sensor is powered or not. At the same time, we can download and we can do a bunch of analytics also on those dashboards. Okay, every vendor will give a customized dashboard or a different dashboard, but we can easily understand whether the instrument is working, whether instrument is online, whether, and we can also download data uh, because we generally use these low cost sensors for dense monitoring networks. Generally, we deploy 100 or a few tens of low cost sensors we deploy. Okay, it is very difficult to go to each and every instrument and download data. That's why Internet of Things is full feature here, and we can access. At the same time, we can check whether the instrument is online or not through these dashboards and through this IoT facility. Okay, now coming to as I said, like these low cost sensors used simplified sensing technologies. They don't use a gravimetric or beta attenuation for particulate matter. Rather, they use optical scattering technique to detect and quantify PM, while they use electrochemical method, metal oxide semiconductor, NDIR techniques to detect and quantify gas sensors. Again, NDIR is again a I also listed this NDIR in the standard technique. Okay, some sensors use NDIR technique. They are realized in very small size NDR techniques, and CO2, CO sensors use still NDR techniques in low cost mode also. Okay, the particulate matter sensors. Most of the particulate matter sensors use optical, means light scattering techniques. The light that gets scattered by these aerosols or particulate matter will be measured, and based on the amount of light that is being measured, we quantify PM in the atmosphere. Okay, let me show you how these techniques works in the next slide. But you can see at the bottom of the slide, I added some sensors. The first one is alpha sense OPC. OPC means optical particle counter, and the second one is plant hour. Plant hour is most common and most famous low cost sensor, and the last one is alpha sense gas sensor. It's a gas sensor. First one and last one are from alpha sense, but first one is particulate matter sensor, and the last one is a gas sensor. Okay, these are the basic blocks that actually work, that actually measures, detects and measures pollution. Around these basic blocks, you need to add a bunch of components to make them operational, to make them unattended operational, to make them work. Okay, these are the basic blocks. You can see these are very small in size. These are actually very small in size. Around it, we need to add so many components to it. Then it becomes a low cost sensor module that I have shown you in previous slides. Okay, what are all the components that needs to be added also? I will show it to you at the end. Okay, just a very basic schematic how optical scattering technique works. Like you see the inlet and outlet where the particles will be entering. Okay, the how the particles enter. That is again, I can tell you how it works in next slides. Okay, the particles enter the optical chamber, and you have a diode laser. Laser, it can be a diode laser, anything. A laser which emits a monochromatic light, and these particles in the optical chamber will scatter light, and at a particular scattering angle alpha, you detect this scattered light, and more light is more particles. Okay, generally these optical, we call it as OPC in the previous slide I was on OPC, optical particle counter. Generally low cost sensors count particles in different size bins, and using a standard density and assuming the particle is spherical, they convert the number into the mass. Okay, based on the photo detector detected light intensity and pulse width and pulse intensity, they count in the particles into different size bins. Okay, this is how PM is quantified in low cost optical scattering technique method. When it comes to the gas sensors, either we use electrochemical or semiconductor method, but mostly we use electrochemical method. In electrochemical method, we have a sensing electrode and a counter electrode. When the gas interacts with the sensing electrode, the ionization happens and the ions flow through electrolyte, while the electrons will measure how much current is passed to the circuit. Based on the current, we convert that into the target mass concentration. Okay, in the semiconductor method, we have a metal oxide upon a semiconductor layer, and generally we heat the semiconductor, then a chemical reaction happens when the target pollutant comes in contact with the metal oxide layer. And what happens is, due to that chemical reaction, the resistance of this semiconductor changes. We know these are semiconductor, the resistance of the semiconductor changes. When the resistance changes, then there will be change in the current, and that current, how much current flows, that is um, uh, quantified as amount of uh, pollutant gas that is being interacted with the metal oxide layer. This is how we generally quantify gas pollutants through metal oxide semiconductor method and electrochemical methods. Okay, then obviously there will be so many challenges with this simplified sensing technology, with this portability and all those things. You might have guessed there will be a lot of so many challenges with this low cost sensors. Okay, first thing is data imprecision and inaccuracy. Okay, actually, inaccuracy is incorrectness, impression is inexactness. Actually, that got swapped. Sorry for that. Okay, data inaccuracy. Okay, the sensor data can be inaccurate, means the values that these sensors provide may be not comparable, or may not be exactly matching with the gold standard measurement. That is called data inaccuracy. That is called incorrectness. And imprecision, like imprecision is like a repeatability. Sometimes if you have a bunch of low cost sensors, if you operate together, maybe different low cost sensor will give you different answers, and due to the error or uncertainty in the low cost sensor components, this data imprecision also happens. Okay, possible non-linear response. Okay, uh, I said like data inaccuracy and impression. In order to quantify whether the data is accurate, whether the data is precise, generally we compare these low cost sensor data with a standard instrument next to. Okay, we call generally field collocation. What is a field collocation? Is we will have these standard instruments in against that standard instrument. We collocate, means we install next to it a low cost sensor, and we try to compare the data between these two instruments. One is a low cost sensor, one is the standard instrument. Okay, whether it is a BAM, whether it is a TOM, whatever. And we will try to see whether both the instruments are giving the right same values or not. And we believe in this standard instrument data. Okay, sometimes the relation between the standard instrument data and the low cost sensor can be non-linear. Okay, I will show you an example in the next slide. And these low cost sensors can be sensitive to environmental properties like relative humidity. Here I just listed humidity. I explained that PM generally we measure its dry mass. We don't measure in the liquid phase wala PM. We measure dry mass. Okay, means generally we heat the sample to remove the moisture. In reference grain instrument, we remove the moisture and we measure only dry mass. But in low cost sensor, we generally measure at ambient humidity level. Okay, high humidity levels, we all know that there will be hygroscopicity and the particle can grow and the particle can scatter more light and it can be overestimated. Okay, that is one sensitivity to environmental property. Okay, again, the low cost sensor measurements can be sensitive to aerosol microphysical properties. Okay, 1 minute, once. Okay, these aerosol microphysical properties like size, composition, in a way, like the light scattering, we all know, like it depends on the refractive index of the target material. Okay, here aerosol is the target or particulate matter is the target. If there is a change in its the particle size, the particle shape, or the number size distribution, or the composition, like more scattering, more absorbing, all these things can lead to different signal in the low cost sensor. That's why these low cost sensors are sensitive to aerosol microphysical properties. Okay, size, shape, composition, kind of thing. Okay, okay. Again, the humidity also impacts the size only. Humidity, if there is hygroscopicity of the due to hygroscopicity, the particle increases in size due to condensation of water vapor. Again, it impacts the response of a low cost sensor. And as I said, like these low cost sensors, generally we always check the data against a standard instrument, whether the data from low cost sensor is um, reliable, or how much is the bias in the low cost sensor compared to the standard data sets. Okay, if suppose if we generally if we find some bias or some kind of an error in the low cost sensor, we generally use a correction factor to correct the low cost sensors. Okay, okay. What happens is sometimes these correction factors, if we derive for one location, it can be different for a different location. Okay, because the I told you, like aerosol microphysical properties can influence the low cost sensor signal. Okay, in such different locations can have different aerosol microphysical properties or particulate matter microphysical properties, and these correction factors can be different for different cities or different places. Okay, okay. Again, there is another tweet, like again, the aerosol microphysical properties, environmental conditions also change with season. That's why if there is a correction needed, that correction factor can be different for different seasons. Okay, that's why this is one big difficulty, one big challenge is these correction factors. Maybe if we try to use some literature derived correction factor to correct our low cost sensor, that might not work, because maybe that correction factor is derived for a different geography. Okay, another one is this degradation. We call it as age factor. Okay, with age with age, these low cost sensor degrade, means their performance can go down. Okay, again, the performance of low cost sensors in highly polluted areas can be different compared to low cost sensors that are operating in a low polluted area, less polluted area. Okay, in highly polluted area, there is a chance that this low cost sensor can degrade faster compared to means like uh, if a sensor that is installed in highly polluted area can only last for 1 year before it malfunctions. A sensor that is installed in low pollution area can go for 2 years or 3 years. Okay, this is called degradation before the instrument sparks off or before the instrument malfunctions. Again, there is a continuous or uh, uh, degradation in its performance. The data also loses its accuracy or precision over time.
Shrikant, before we go on to next slides, we have two questions. I think it would be
Yeah.
good if we can address now. So Shika has a question. What about the accuracy of low cost sensor? Because you were talking about like how far it is accurate, and we have one more question here. You were talking about field collocation. Like how are the LCS calibrated on field?
Okay, okay. Maybe that are the exactly my next slides. Okay,
Okay.
maybe next slides. These questions these are will be resolved. Okay,
Okay.
that's fine.
Yeah, sure. Thank you.
Okay. Now here I just want to tell you what is accuracy and what is precision. Okay, what is accuracy and what is precision? Like, see, as I explained it, accuracy is how close your low cost sensor measurements to a standard in reference grade instrument measurements. Like how far is your test measurements, how close is the test measurement is to a true value. Okay, that is called accuracy. How far? Okay, in the first panel, in the left panel, you can see, okay, you can see there's a reference method and test method. Just consider this test method as the low cost sensor and reference method is your reference grade instrumentation. And the red color line is your 1:1 line, y is equal to x line. You can see all the data points are very close to the y:1 line. Okay, but they are scattered. You can see the r square value is 0 0.8 and your error value is around 1.42. Okay, then on the right hand side plot, if you observe, uh, the points are not close to 1:1 line, but they are very close to a linear fit and they are very close to each other. Okay, in the first plot, what I can say is the data is more accurate and less precise because they are not close to each other, but they are close to the standard value. In the second plot, you can see the r square is very high because they are very close to each other, but you see the error, it is 2.5 to compare higher compared to the first plot. Okay, in the second plot, what we can see is they are more precise than accurate. Okay, this is how precision and accuracy is defined. And as I mentioned that sometimes there will be a non-linear response for this low cost sensor. You can see on the y-axis, which is PMS 2. PM 2.5, which is a plant hour based measurement. On the x-axis is a reference instrument. Uh, you can clearly see the variation in the data. They are following a non-linear pattern. Okay, a linear fit is not able to explain the variability. You can see the linear fit r square is 0.825, while an exponential decay fit or exponential fit has better r square, which is 0.92. An exponential fit is able to explain the variability better in the data. Means here the non-linearity you can observe the data, the low pass sensor data follows a non-linear trend with respect to reference instrument data. Okay, so as I said, like there's imprecision and inaccuracy. Sometimes this imprecision or the error gets reduced if you do averaging over time. Like, see, because this error comes from the error generally is random in nature. What happens is if it is random in nature, generally if you average, the error plus minus will get cancelled out and it can more smooth data you can get. Okay, sometimes averaging will help. Hourly, you can see on the left side hourly measurements, low cost sensors versus a BAM. On the right side you can see daily measurements. You can see on the hourly measurements there's a lot of scatter, while daily measurements if means the hourly values are averaged to 24 hours, then you get a better smooth variation. Okay, the error generally gets cancelled out if you do averaging. Okay, now coming to the co-location. Now, as I said, most of the low-cost sensors are generally factory calibrated. They check their performance in the factory by injecting a synthetic or a particular type of aerosol, and they see the response and they calibrate based on some particular type of aerosol. But when you deploy it in the ambient, the composition of the particulate matter can be very different. The cocktail everywhere it is different. It is a cocktail of various the composition changes. That's why even it is a new low cost sensor, it is always advised to compare its data with a reference instrument, where we call it as field collocation. Collocation means uh, installing them side by side. Okay, in the field, in the here the field is nothing but in the ambient atmosphere. Suppose if you are doing some measurements in Delhi, it is always better to conduct your co-location in Delhi and test its accuracy, and if needed any correction, derive the correction factor and apply the correction factor on the low cost sensor data to derive some meaningful information, okay, from the low cost sensor data. Okay, in this photo you can see there are three BAM instruments, beta attenuation monitor. These are all BAM 1022 monitors, which are like standalone monitors. Those doesn't require any shelter. Okay, on the right side under the table we have a bunch of low cost sensors. We are trying to measure the ambient air pollution next by these reference instruments and the low cost sensor installed next to each other. Okay, now you see what I did is I have some 10 different low cost sensors and I collocated, means I install these 10 different low cost sensors next to beta attenuation monitors and I compare the data against all the low cost sensors against the reference instrument, which is nothing but our beta attenuation monitor here. See, I use 10 different low cost sensors, means 10 different makes. The sensors are of different makes. You can see all low cost sensors response is not the same with respect to the reference grade instrumentation. Some low cost sensors underestimated, some low cost sensors overestimated, some low cost sensors are much closer to the reference grade instruments. All these low cost sensors used optical scattering technique only, but the response is different with respect to a reference grade instrument. Why? Because see, different low cost sensors can have different optical architecture. Okay, the what wavelength or what laser wavelength that these low cost sensors used, what is the construction of the optical chamber, what is the scattering angle, at what scattering angle the scattered light is detected. All these things can be different for different low cost sensors. That's why the response of different low cost sensors is different. That's why again you need to be very cautious if you are trying to use a literature derived correction factor for your measurements. You need to have your own collocation experiment in your own field location to understand whether this low cost sensor requires a correction factor or not. If it requires, what type of correction factor we need to apply. Those things you need to do it for yourself, for your own low cost sensor and for your own city or for your own field location. Okay, in the earlier slide, what I have shown is different low cost sensors in one particular location. But here in this experiment, what we did is same low cost sensor in different cities. Okay, you can see the first one is Chandigarh, Delhi, Mumbai, Bangalore, and Chennai. Okay, same low cost sensor, same make, which is our Atmos, in different cities in the same period. Okay, then again, we have seen the differences in the low cost sensor performance. Suppose in Delhi it is overestimating, in Mumbai it is underestimating, in Bangalore it is very close to the reference grade data. Why? Why? Because it is the same instrument, okay, with same age, same period we collocated. We performed collocation experiments in 5 different cities. Okay, again its response is different. Okay, why what could be the reason is, okay, the reason is different regions can experience different microphysical properties of this particulate matter, in the sense the sources dominating in that city is different in different cities. Like you can see these are some air shed based upon
Can you go back to the previous slide?
ah
Hare Krishna, do you have any questions on the previous slide? Do you have any question? Sorry, even like which slide? Can you go to the previous slides? This one? You can unmute yourself and ask if you have any graphical slide. You mean this one, the one with the PM sensors? Yes. Okay. You do you have any questions on this? Okay. We have one question by Prince. What metrics are considered to evaluate the performance of LCS during co-location and calibration?
Yeah, there are bunch of metrics like basically we can use R square to see whether the precision in the data to quantify the accuracy. We use generally root mean square error, or in terms of percentages, we can use normalized root mean square error, mean absolute error. It's like this. There are a bunch of parameters. By using them, we can quantify the precision and accuracy of these low cost sensor data sets.
We also have one more question on
Yeah.
the challenges from Abhishek. So it is on the degradation part. So since it is degrading, does it mean we have to calibrate from time to time, or eventually the sensor will get retired after its full degradation? So what is an average time for an Indian
See again.
condition like
Yeah.
Delhi?
Average time, it is very difficult to say. Like, it's not only the pollution level, it's also the weather. Sometimes this harsh weather. Again, see, in my experience, I have seen a lot of low cost sensors in which there are uh, beehives kind of thing. These insects making their nests inside these low cost sensors, because sometimes we don't check for months, then we can see a lot of insects making their nests inside the low cost sensors. These kind of things we have observed earlier. Okay, it also the harsh weather. Okay, the high pollution, the high pollution episodes, and all these things can degrade the sensor performance. Okay, suppose if it is a multi-sensor experiment, it is always good to have one sensor next to a reference grade instrument, means in collocation throughout your throughout your experiment or throughout your deployment time. Okay, thereby you can understand if there is any changes in the correction factor time to time, if there is any change in the correction factor seasonally, all those things can be derived if you use one sensor next to a reference instruments throughout your experiment. Like, if your network is intended for 1 year, just spare one sensor next to a reference instrument throughout that 1 year. Then you can calculate your correction factors on a seasonal basis, on a monthly basis, and apply on rest of the sensors in the city. Okay, that's how we can do this collocation experiment. At the same time, some, if it is a rapid deployment, short-term deployment, before deployment of the sensors and after deployment of the sensors, you can collocate, and you can see whether there is a change in its performance, whether there is a degradation in the sensor performance. This way also people do.
Thank you. I think you can continue. We have some questions we'll take up at the
Yeah, yeah. See, basically, what I'm trying to say is, like, in different locations, the sensor response is different, different cities, because the aerosol microphysical properties are different in different cities, because the source dominance is different in different cities. One of the main challenge, as I said, is sensitivity to aerosol microphysical properties. That is what the reason for this different response of these local sensors in different cities. This is some airshed demarcation based on source dominance. You can see the green color area of India is dominated by coal-based emissions, while the yellow color one is dust-based emission, because we have this Thar desert, all those things. Again, the Indo-Gangetic plain has a lot of residential biomass. Those, that's why the sources are different. Means the aerosol microphysical properties also can be different. That's why, as these low cost sensors, as the optical scattering technique is more sensitive to the aerosol microphysical properties, the response of low cost sensors in different cities is different. Okay, even though we use the same sensors, we we did the experiment in the same time of the year. Okay, here I just want to show is the contribution of different sources to PM 2.5 is different in different seasons. Okay, so if sources are different, means the aerosol microphysical properties are also different. That what I want to tell is, with season also, the correction factor or the response of low cost sensor can be different with respect to reference grid instrument. That's why we might need uh, temporal correction factors, means like temporarily varying correction factors, seasonal correction factors, monthly correction factors we might need to derive, because due to the sensitivity of low pass sensors to aerosol microphysical properties, and the sources during different seasons they differ, and with sources the aerosol microphysical properties also differ. Okay, here that's about the challenges that we generally face with the low cost sensors. I talked about inaccuracy, imprecision, sensitivity to aerosol microphysical properties, collocation experiments we need to do. Okay, degradation, all those things. Now I just, in the next two slides, what I want to say is I want to give a flavor of what all different components that a low cost sensor module is module needs. Okay, we have seen this alpha sense and plant our basic measuring blocks. Okay, upon that, or to those building blocks, we need a bunch of components to make a low cost sensor module. Okay, first thing is we need power. Okay, these are small building blocks that need some the power is very small, some small DC power is enough, but we need to power the sensors. Then we need to have a power supply system in your low cost sensor module. At the same time, we need some what you call a communication module. As I said, these low cost sensors mostly work on Internet of Things. Okay, to communicate the data, we need some arrangement, like either a SIM card module or a Wi-Fi module. Some people use LoRaWAN, some people even use Bluetooth technology. Like if you go very close to the low cost sensor through to computer, you can connect the sensors to your computer and download the data. Okay, they use Bluetooth for short ranges. Okay, some people use LoRaWANs. Okay, some people use Wi-Fi. If in Western countries, where the street Wi-Fi is there, generally they connect it to the street Wi-Fi, or where everywhere Wi-Fi is available, they connect it to Wi-Fi. But countries like in India, we generally use a SIM card module. We put a SIM card and data with the data plan, and we try to uh, push the data to cloud server using this internet. Okay, again, we need this signal conditioning. Like sometimes the signal that is the voltages that these low cost sensor produce very small, then we need some kind of amplifier, some kind of analog to digital converters. In addition to pollution sensors, we also measure some environmental parameters like temperature, humidity, sometimes barometric pressure also we measure. If you want those measurements also, we need to have sensors in the module, those particular sensors also. Okay, in the figure that we can see, there is an anemometer attached to the low cost sensor. Anemometer is to measure wind speed and wind direction. The anemometer that here is shown is a sonic anemometer. It works on ultrasonic principle. That's why there are no moving parts like cup and vane. But this anemometer, if you want to measure, in addition to the pollution, some wind fields also, we can attach that anemometer also. Again, we need a proper enclosure and housing. We need IP protected enclosures, IP protected, IP rating. IP rating means ingress protection. IP stands for ingress protection, protection to dust and water. IP rating is required, like whether the sensors can be installed, can be operated during rainy conditions. That kind of enclosure you need. Okay, again, to run the whole system, we need some firmware, we need some software. At the same time, we need some uh, cloud storages, servers to store these data sets. These are all different components that you need to construct or to assemble a low cost sensor. In addition to the basic sensing element like a plant tower or alpha sensor, you need to have all these components to be added to make a operational low cost sensing module. Okay, and this is last but not slide of my presentation here. How to select the right sensor. Okay, suppose if you are planning to deploy a sensor network, or if you are planning, suppose if you are planning to buy a sensor, what are all the things that you need to look at to choose the right. Okay, first one is your objective. Okay, the objective, what you are trying to achieve. This is very important while choosing a sensor, because first of all, what what are all the parameters that you want to measure first. Okay, that is important. Then you need to identify, okay, I need PM, I need NO2, I need SO2. First, we need to identify all this pollutants list. Then we need to make sure the sensor that you are going to purchase has all these sensing elements. Next, what is the purpose of the data? When you are trying to um, identify, or when you are trying to choose a sensor, you need to make sure for what purpose you are using that data set. Suppose if you are trying to measure exposure, then you need to personal exposure. Then the instrument should be very compact, wearable. Suppose if you want to use it for citizen science experiment, then the sensor should be easily operatable, like it should be a plug and play kind of instrument. Suppose you are using it for mobile monitoring, the sensor should be robust against the vibrations, because on the moving platform generally sensors can subject to vibration. Suppose that's how we need to, first we need to uh, I, see what pollutant that you are going to measure, and what, for what purpose the data is being used. That should be your first thing. And next thing is, suppose now I have identified my pollutants. Now, whether for, suppose for CO we can use metal oxide semiconductor and NDIR also. Okay, then what particular sensing technique is better for that particular pollutant, or that's why I call it pollutant specific sensor suitability. Okay, suppose if you want to measure CO, okay, NDIR technique is always better than, in metal oxide semiconductor also can measure CO, but NDR measured CO is much better. Okay, then what are all its performance characteristics? Suppose what is its limit of detection? How low it can measure? What is its response rate? Suppose if you are going for a mobile monitoring, you need every 1 second data, or every 5 second data, every 10 second data, because you are on a moving platform. Okay, whether the instrument has that response rate. Okay, whether the instrument can give that fast data set. Okay, again, accuracy. Generally, the low cost sensor vendors or the low cost sensor assemblers will give you a specification sheet. In the sheet you can see how accurate is the data that is being produced by this sensor. Again, linearity, whether it is following, again, you can ask the vendor whether the sensor has the linearity with respect to reference instruments or not. Okay, this is also one important thing when you have to check when you are choosing a sensor. Again, the environmental robustness, like how robust is this instrument, whether it can withstand harsh environments or not. Okay, what is the dynamic range of the sensor measurement? Whether in a high pollution episode, like suppose if the PM 2.5 goes to 1000 or 1500 microgram per meter cube, whether it can measure it or not. This kind of environmental robustness also you need to see. Calibration and correction. Okay, we know, like from the vendor we might be understanding, okay, this is the accuracy and this is the precision, but whether those experiments were conducted with a synthetic aerosol, or a one particular type of or monodisperse aerosol, uh, the accuracy measures are given based on what type of aerosol we need to check, and based on that we can decide whether the sensor requires a field calibration or not, or field collocation or not. Okay, then we need to perform a field collocation. Then again, deployment context is like static versus mobile versus personal versus citizen science, all those things I explained. Like if it's a mobile, it should withstand vibrations, it should have fast response rate. If it is personal, it should be compact, and it shouldn't have it's in personal also we need to take care of this radiation, how much the instrument is, how much radiation it is, because that we will be exposed to the radiation of the instrument also. That also we need to keep in mind. Citizen science, how easy the instrument should be operated. Then communication of data handling, like whether the sensor has a SIM card module or not, whether it works on Wi-Fi. Suppose, for example, if you purchase a per player sensor, it has have only Wi-Fi module. It doesn't have a SIM card module. Okay, for Indian context, we might need a GPRS communication, like we need a SIM card. Okay, then we need to identify whether we need to see whether the sensor has a SIM card module or not, and what type of data hosting. Whether we have a local storage, like in like a SD card, like a flash card, whether the sensor can store data locally or not. Okay, whether it can buffer, whether it can suppose in power failures, whether the instrument can store some data set. Again, data formats, whether machine readable formats, uniform formats the vendor is providing, or the instrument is providing machine readable formats or not, easy to read formats. Again, cost beyond capital, because the capital cost is low. We discussed about a low cost sensor, but um, calibration, because everyone will not have a reference grade instrument, right? We need to, if you want to calibrate it, we need to collocate against a reference grade instrument. Then we need to see where the reference grade instrument can is available. If not, maybe we need to purchase one. These are some costs beyond the capital cost. Also, sensor replacement frequency, as I said, it degrades. Sensors are prone to degradation. At what frequency we need to replace the sensor? Suppose it is going beyond correction, the data goes beyond correction, or if the sensors read some 000, or the um, optical chamber gets contaminated, it is showing very high values consistently, or it is going to constant value, then obviously we need the sensor replacement. The sensors are not that costly, but we need to understand at what frequency we need to replace these sensors. Suppose in high pollution and harsh weather conditions, we might need to replace the sensor much frequently. And after sales support, suppose the vendor will be able to provide after sales support, can he come under a annual maintenance contract? All those things we need to consider for selecting a right sensors for your operation. Okay, finally, low cost sensor is really low cost, because we know that reference grade instrument, the capital cost is very high. For low cost sensors, the capital cost is very low. But the advantage with reference instruments is its robustness, accuracy, all those things. For low cost sensor, it is questionable, because we need to conduct our own experiments, and we need to derive its accuracy, precision, all those things. And logistics and data processing, reference grade instruments is very easy. Like they give hourly data, or they give data in standard formats. But in low cost sensors, it is a bit tough, because we the data we get every 1 second, and dense monitoring networks. Suppose if you are getting every 10-second data or every 1 minute data, it will be huge data set to handle. We need data storages. At the same time, we need some coding people. We need some soft skill people to analyze these data sets, because we can't do it manually. Mostly we can't do it manually, because huge data sets it generates. Suppose you have a dense network of monitors, then it generates huge data set. Then what is the main strength of reference grade instrument? It gives temporal data. It due to the cost and due to the infrastructural requirement, we can't use it, like we can't scale it. The reference grade instruments, we can't have a number of instruments deployed, or a number of stations deployed. But low cost sensors, due to its portability and cost effectiveness, you can scalability is one of the advantage. Yeah, this is a overall perspective of low cost sensors, where low cost is really low cost, but we need some cost in addition to the capital costs. We need some cost in terms of manpower, in terms of computations, or in terms of storage, cloud storage. For these things, we need to put some cost. Yeah. Uh,
Thank you
Yeah,
so
I'm done with with my presentation, Abhinaya.
Thank you so much for a very detailed overview of low cost sensor. I think it was you have given like a very clear overview of how the low cost sensor works. Like I think the details of in our future sessions we'll also discuss in detail about a lot of other aspects. And now I would like to take a few questions. Rafiq has a question on if we deploy a 10 low cost sensor which is of same type and we are calibrating it against a reference grade instrument, is it also recommended to do an inter-sensor calibration like between the 10 sensors that we have that he has installed? Is it required to do an inter-sensor calibration?
Yeah, because I touched upon a topic called imprecision. Okay, sometimes these local cells, if you have 10 units and if you operate all 10 units together, they can give 10 different, or they can, some sensors can give different values. That's why it is always good to do a intersensor collocation first. Before, my suggestion is like before going to a reference grade instrument, maybe we can collocate all the 10 sensors together and see the data whether all the sensors are giving the same number, because when you collocate each other they are supposed to give the same value. First you see inter device comparability. Suppose if the sensors are not matching with each other, then it is better to collocate all 10 devices against the reference grade. Then you derive sensor specific correction factor. Okay, suppose if all 10 sensors are giving the same value, then obviously you can choose one or two and we can collocate and you can apply, or you can transfer the same calibration equation for all 10 devices. It is always good to check intersensor um, comparability with low cost sensors.
Thank you. I think Prince has two questions. Prince, would you like to unmute and ask one on the best instrument for PM monitoring and other on the calibration algorithm? Like, would you like to unmute and ask?
Hi, Sreekanth. So this is Prince from CEW,
Ah,
and thanks for the beautiful presentation. So my question is on the reference monitors. So you mentioned in the starting there are three kind of reference monitors which monitor PM 2.5. So can you tell me what is the best monitor?
ah,
I mean,
for
yes,
for reference grade measurements, right? It's not for
ah, yes.
every instrument has its own, or every technique has its own limitations. Okay, suppose if you want continuous data, obviously you need to
Mhm.
go for either a beta attenuation monitor or a TEOM. Okay, tapered
Oh,
element oscillator. Gravimetric is the gold standard. We call it as a federal reference method. That is the gold standard. Even this BAM and TEOMs are compared against gravimetric for US EPA certification. Okay, okay, it depends like whether it's okay if you have time integrated measurements like 24-hour mean or 12-hour mean or 8-hour mean, then you can go for gravimetric. Okay, suppose your requirement is continuous measurement, then you need to go for beta attenuation. Or but all the measurements using any of these three techniques are considered as reference measurements, and you can be used for compliance enforcement and legal purposes.
thanks for the clarification. I have one more question. So so which calibration algorithm did you use in this study? And
For the low
second
cost
is,
sensor, right? This question is for,
yes,
okay.
yes. And
See,
what are your views on machine learning algorithm we use for calibration?
if you see, there are very simple linear correction methods. First of all, we need to see there is US EPA guidelines, performance metrics for low cost sensors documents are there. Okay, first we need to understand whether it requires a correction or not. Then, if it requires a correction, I think it is better to start with simple linear correction to, you can explore. See, I also have 3 4 papers exploring simple corrections to machine learning based corrections. Okay, but
Mhm.
in my view, you should start with simple model, then you can increase the complexity of the model. If you are not able to achieve your target accuracy in the data, then you can obviously keep on exploring complex models up to machine learning, random forest, support vector regression, anything you can go up. Right. Okay, but always it is an exploration. Like you need to develop and you need to see whether you are able to achieve that accuracy in the data by using that particular model.
Thank
Thank
you
you.
so
So,
much.
yeah, thank you, Prince and Sreekanth. So, you just mentioned, Sreekanth, that generally manual monitors will be compared with the BAM for some regulatory reporting. So, Arsh have a question. Like we since reference grade monitors are used as a benchmark for validating sensors, do we have any standards or oversight mechanism to ensure the regulatory grade monitors accuracy and its long-term performance and accountability in the Indian context?
Okay, he is trying asking about regulatory monitors accuracy, right?
Yes, yes.
Okay, suppose suppose if you take a BAM, okay, BAM is USCPA identified reference instrument. It is called a federal equivalent method. There are two types here: federal reference method and federal equivalent method. This geometric method, where you directly measure mass, that is federal reference method. Okay, BAM and TEOMs are called federal equivalent methods. Okay, uh, when USEPA gives a certification, then there will be so many things notified in that certification. If you follow this protocol, if you follow this, then only the data from this instrument is considered as a reference measurement. Okay, even though the BAM gives you 1 hour data, but if you properly read that USEPA certification, it clearly mentions that 24-hour averages value are only certified as reference data, provided if the instrument is equipped with a heater, provided if you consider only hourly channel data, provided if you uh, do routine maintenance as per its manual. Okay, if you do maintenance as per the manual given frequencies, and if you maintain that instrument properly, then you can use the data for what you call reference or enforcement or compliance purposes. It's like you have to maintain it. That's all. As per the manual, you have to maintain. Then you can use the data.
I think the
Uh,
question is on how the like in what are the standards and oversight mechanism ensure accuracy of the regulatory monitors? Like, is there any standards in the Indian context?
there's nothing like Indian
Okay.
context. See, generally we perform lot of calibrations to the instrument. First thing, we do a flow calibration, we do zero checks, we do span checks. These are all the mechanisms through which we ensure that everything is doing, because other major components, they will have a lifetime. Okay, if it is a photo scintillation detector, or if it is a beta particle source, they will have a lifetime. Okay, but
Mhm.
as per the routine calibration or maintenance purposes, there are we need to do all this zero calibration, flow calibration, span calibration, all those things. If all these things get passed, then the instrument data is considered to be accurate.
Okay. I think we are on time now. We have two more questions.
Yes, yes.
Yeah, one from Abhishek. Do we need to apply the correction factors ourselves, or will the companies will automatically update the correction factors based on the
Again, it
calibration?
depends. Most of the low cost sensor assemblers are very um, like customized things they provide. Suppose if you tell them, okay, this is my correction factor, can you put this in the back end and give us a corrected data? They can do. But at the same time, suppose if you have the correction factor, like in hand, you can do it offline also. You can apply the correction factor on the field collected data. But most of the local sensor vendors are very um, they can provide customizable dashboards. Some people will give some place to add these calibration coefficients, and then data will be automatically corrected. All those options can be explored.
Sir, hi, excuse me, sir.
Hi, Arani, you can ask your question.
Okay, so about the classes, this research program. So when please give me the dates for the class. I need the exact dates when will occur. When will this meeting will occur? Is it daily or like
I can share the link on the chat box. So it is planned to have a weekly once.
okay, sir.
Yeah, you can find the details here and
Okay,
share it on the chat box.
okay.
Yeah, thank you.
Okay, so it's weekly once every Monday, right?
Yeah,
Tuesday, I
yeah,
think.
Tuesday. Yeah.
Every Tuesday.
Yeah, you can check the agenda. I've shared it on the link in the chat box.
And another doubt:
Mhm.
does LCS observe the has the ability to observe the nicotine which has been exposed in the air?
Yeah, Harini had a question. Like, does the LCS that we used for monitoring has ability to absorb the pollutants like nicotine present in the air?
I don't think so. See, this nicotine, you see, nicotine can't be measured directly. It can be measured in a different form like code 9. Okay. I don't think these LCS are having that capacity to measure that, because we need to go for some mass spectroscopy kind of measurements to quantify those things.
Oh, so these air purifiers are able to focus on the third hand smoking or the third hand air pollution. So not the
The
first ones.
purifiers will have generally two types of filters. One is a activated charcoal, another one is a HEPA filter. HEPA filter is for removing of particulate matter, and this activated charcoal is to absorb some gaseous pollutants and VOCs kind of thing. That's all they have.
Thank you. So one final question, like what makes a monitoring network like the LCS, or what makes a monitoring network representative for a city or a region?
Oh, that is very
Yeah,
debatable question. There's a lot of papers published on that. Okay, I think I can't give
yeah,
that answer in a
yeah.
straightforward way. Okay. Because there's so many papers published on the topic. Maybe you can refer papers.
Yeah. One more question. So, is there in terms of PM, like does this PM 2.0 to PM 10 ratio is still considered for understanding if the sensor is performing good or
No, one thing what I want to give you a caution is you need to be very careful while measuring PM10 from using a low cost sensor, because generally PM10 are much bigger size particles, like 10 microns below. Okay, what happens is these low cost sensors generally don't use a standard pump to suck the particles. Rather, they use a fan. Okay, the fan to draw the air sample into the sensor optical chamber. Okay, these fans will have very less aspiration efficiency. That means they can't they can't draw effectively larger particles. That's why low cost sensor PM10 measurement is always questionable, and some people there are papers that recommend not to use PM10 measurements from low cost sensors because the uncertainty is too high in PM10 measurements. No, we can't use PM10 2.5 to 10 ratio, because the uncertainty in or the error in both the measurements is not the same, and the PM10 measurements from low cost sensor will have a lot of error in it or bias in it.
I think I think we are done with all the questions. If you have any further question, feel free to write to us. Thank you, Sreekanth. Thank you so much for taking your time. Like it was a 1 hour long presentation. Thank you so much
Yeah,
for
that's all
doing.
fine. That pleasure is mine.
And also thank all the participants for joining us today. And this is going to happen in 5 parts, so we have 4 more sessions. Like the slides and the recording will be made available in the link that I've shared in the chat box now. Thank you all.
What I suggest to the participants is try to continue attending all the 5 sessions, because this is a series and every presentation is interconnected. Like I gave only a overview. Actually, the next presentations will be much more important because they directly handle with the data techniques, all those things. That's why I maybe the calibration, co-location, all those things will be dealt in detail in next presentations. That's why it is better you guys continue and complete all 5 sessions. Yeah, that is my suggestion.
Thank you. Thank you so much. Thank you, Sreekanth.
Yeah.
See you all next time in the next session.
Bye.
Thank you. Bye bye. Have a nice day.